So welcome to another lecture. In this lecture, we'll be doing IGCSE Chemistry Extended. We'll be doing the chapter Chemical Energetics. What I've done in this lecture is I've taken the past papers. Mostly these questions are from 2025 board papers. So there's a list of around 20 to 25 questions that I've taken. And how I have arranged the lecture is that, all questions of each type from chemical energetics are asked. But basically, before I start the question, there will be two kind of questions which will be asked. One would be in chemical energetics. One would be a question of some sort which will be based on this these kind of graphs. Energy of reactants, energy of products. You will have to identify whether it's an exothermic reaction or endothermic reaction. This is one kind of question which is asked. Usually, they are asked in the MCQ. And the second type of questions which are asked are where you have to calculate the enthalpy of the reaction. So what I've done in this lecture is I have taken both the kind of questions. I have taken questions which are graph based. In graph based, they'll ask you about the exothermic, or they'll ask you something about the activation energy. The graph based questions. So I've taken different kind of MCQ so that you understand the kind of question which are asked. And then I have taken, I have solved 4 or 5 numericals also. These numericals are simple. They don't require much of understanding. A basic prerequisite of chemical bonding is required. So this lecture would be, I think, about half an hour or so, 30 to 40 minutes. I'll try to make this lecture. And but before I start, I want to just spend 2 minutes. I'm assuming that you have some knowledge about this chapter, because this is sort of a revision chapter. So some basic understanding. Just to start, I'll give you few inputs that you can understand. You can assume that the reaction is reaction to be a sort of system. Now remember, when we take reactants, we have to break the bonds of the reactants. So for example, if I take a simple example, C plus O2, CO2. Yeah, so let's take this combustion reaction. Now, when I have to break the bonds of oxygen, there will be energy which will be required. So EB would be required to break the bonds. This energy would be entering the system, and the energy which is required to break the bonds of the reactant is considered to be positive. On the product side, when the products are formed, whenever new bonds are formed, energy is released. And because that energy is released, because that energy would be leaving the system. So this EF, what I'm trying to tell you is this is the energy of formation. This is the energy of formation of new bonds. This EB implies breaking the bonds of the reactants. So bonds of the reactant would be broken. And when new bonds would be formed, when the products would be formed, then energy would be released. Energy would be entering the system. Energy which enters the system is considered to be positive, and energy which leaves the system is considered to be negative. Of course, it has to be considered to be negative. Now, few of the students get very confused about endothermic and exothermic, but it's very simple. I'll try to make it as simple as it possible. See, endothermic reaction are reaction where energy is absorbed. Net energy is absorbed. So what that implies is that the energy, you can look at these kind of reaction like this, that when the bonds are being broken, when energy is being taken, the positive energy is more than the energy which is released when the new bonds are formed. So if energy required to break the bonds is more than the energy which is released when new bonds are formed, so net energy is absorbed by the system. And these kind of systems are called endothermic reactions. Another way of looking at, if you want mnemonic, if you are still confused, so endo can use a mnemonic in, energy in. So in these kind of reaction, what will happen is, I'll also explain from the graph side. What will start happening is that the energy of the reactants, when because net energy would be absorbed by the system. So you can look at another way of looking at it is that net energy is absorbed by the system. The energy of the products is more than the energy of reactants. So this is another way of looking at these reactions so that you can understand. So this is how the reaction this is how the graph of the reaction would look like. So this is the activation energy. This is the activation energy represented by EA. So here the delta H, that is the enthalpy, would be positive. So in endothermic reaction, the energy would be positive. So try to see what is happening. So net energy is being absorbed. The delta H is positive. So that is what is happening, and the graph looks something like this. Now, if you understand this, you'll be able to answer the MCQs also, which will be graph based. And if you understand this, you'll be able to do the numericals also. When I'm doing the numerical in this lecture, I have again explained this again and again. The second kind of reaction, of course, which we know is exothermic reaction. Now, in exothermic reaction, the best way to understand a exothermic reaction is a combustion reaction. This is a very basic reaction that you can understand. An exothermic reaction is a combustion reaction. Combustion reactions are the best examples of exothermic reactions. In these kind of reactions, what will happen is that energy is given out. Energy is given out. So energy is absorbed to break the bonds, but when the new bonds are formed during the formation of the products, the energy which is given out is more than the energy which is required to break the bonds. So that is why this is written here that the energy which is given out, which leaves the system, is more than the energy which is absorbed by the system, the net energy. And that is why the graph would look something like this. That the way of looking at it is that energy of the product would be less than the energy of the reactants, the bond energy of the reactants. And here the delta H would be negative. Here the delta H would be negative. Now, so exo, the mnemonic that you can follow is X, exit. Net energy is exited. I'm using again and again, the word that I'm using is net. You need to understand net. Here the delta H would be negative. Delta H would be negative. The enthalpy would be negative. Now, I hope you are able to understand this. If you are able to understand this basic introduction, then you will be able to do the graph side questions also. You will be able to do these bond, calculating the bond questions also. Here also the same things are used. So if you see, again they are graph-based question has energy, progress of reaction. They ask you to label. This is activation energy. So this is so basically these kind of questions would be asked. So let's start. So the first question: water is added to anhydrous copper sulfate in test tube. Mixture becomes hot. Which type of reaction and reaction pathway diagram applies to the reaction? So mixture has become hot, so it will be an exothermic reaction. Why exothermic? Because net heat is being given out from the system, as has been explained before. So we started with some bond energy of the reactants, and because heat has been given out, heat has exited the system. So that is why the energy of the product is less. So that is why this is a graph which will represent the exothermic reaction. Okay, next question. Reaction pathway diagram is shown. There are reactants, there is products. Now, if you look carefully at this reaction, the products have higher energy than the reactants. So, energy would have entered the system. Net energy would have entered the system. So, another way of looking at it is that from the surroundings, the system would have absorbed some energy. When this happens, so the question which is asked is which row identifies the type of reaction? So the type of reaction, because net energy is being absorbed from the surrounding, the type of energy would be type of reaction would be endothermic, and how the temperature of the surroundings change. And this is the point that I'm trying to make, because the system is absorbing energy from the surroundings. The temperature of the surroundings will decrease. The temperature of the surroundings will decrease because the system is absorbing the energy from the surroundings. The energy of the product is more. So in these cases, as you understand, delta H would be positive. H would be positive. In the previous case, in exothermic reactions, remember, enthalpy change is negative. Now, usually these kind of calculation questions come in the numerical part, but they have asked this in MCQ. The average bond energy of CH bond is 413 kilojoule per mole. What is the enthalpy change when is formed? Methane molecule is formed from carbon and hydrogen atoms. Now, for this reaction, for these kind of questions, you should have a basic understanding of chemical bonding. So, for example, you should understand first that the formula of methane is CH4. Then you should also understand that this is how the bonding of methane looks like. Now, in this chapter is fairly simple chapter, but this chapter might become difficult for the students who don't have even a basic idea about chemical bonding. So then it will become difficult. So once we understand that methane has 4 bonds, 4 CH-CH bonds, 4 CH-CH bonds. Once we understand that, and we also understand that 1 mole of is being formed. So this is the amount of energy which will be releasing the system. So what I'm trying to tell you is that average bond energy of a CH-CH bond is 413. Now, when molecules are formed, every time a molecule is formed, energy is released. So, when energy is released, it leaves the system, the energy is negative. And when 4 bonds are formed, so it will be minus 4 into 413. Hope this is making sense. 4 3 the 12, 52, 16. So, minus 1652 kilojoule of energy is released. Adding a catalyst, it's a rate of reaction numerical, but here delta H was used, so that's why I included here. This statement describes the effect of adding a catalyst to a chemical reaction. See, a catalyst, I won't be going into detail. I have another lecture where I have covered the rate of reaction questions. But when you add catalyst, the delta H doesn't change. Remember that. The enthalpy of the reaction doesn't change. Exothermic reaction, sign of enthalpy is negative and temperature of the surrounding increases. Why? Because heat is lost to the system. Like previously we were saying, in endothermic reaction, we absorb net heat from the surroundings. That is why the temperature of the surrounding decreases. Okay. A reaction pathway is shown. You have to label X and Y. See, when I look at this reaction, I understand that the energy of products is more than the energy of reactant. So it will be an endothermic reaction. Net heat would be entering the system. That is why the energy of the products is more. Bond energy of the products is more. Delta H would be positive. So this Y is the enthalpy and this X is the activation energy. This is the symbol of activation energy which is used in the textbook. I had looked at 1 mark question asked in your board exams in 2025. They had asked the symbol of activation energy. So you should be clear about the symbols also which are being used in the textbook. So X is the activation energy and Y is the enthalpy change, and this is a endothermic reaction. Next question. I have done this numerical. This numerical is also done. That is on the second part of this. Reaction pathway for the reaction PQ to form RS is shown. Which letter shows the enthalpy change for the reaction? So, see, this is the energy of the products. This is the energy of the products. This is the energy of the this is the energy of the reactants. This is the energy of the reactants. This is the energy of the products. B is the activation energy, as we have done before. And this C, the difference of the energies of the product and the reactant, this C is the delta H. And here again the delta H is positive. So the answer would be C. Again, the numerical is done in the second part. So these are the MCQs which were asked. The graph-based MCQs which will be asked. And now I'll start with the numerical part which are usually asked in the chemical energetics. Question where we have to calculate the enthalpy in a reaction. This is the rate of reaction chapter. So equation for the complete combustion of methane is shown. Now, before even I start doing the calculation, there are few simple things that I need to understand. That because this is combustion, there will be energy which will be released because it's a combustion reaction. So we understand that in combustion, energy is released. So we understand that if I consider this to be the system, then net energy would be leaving the system. And whenever the energy leaves the system, basically the energy of the system decreases. Inside the system, the energy has decreased. So that is why, and we know that when energy is released, leaves the system, that delta H is negative. Delta H is negative. So our answer should be negative, and that is what is seen in 3 of the choices where the the answer is negative. In only one, the answer is positive. So we can safely assume that this won't be the answer. Now we have to select among these 3. So for this, we will do the calculations. We'll start doing the calculation. But I wanted to make this clear before even we start doing the calculation. Now, when we start the calculation, we understand that EB would be the energy which will be required to break the bonds of the reactants. So, one way of looking at this is that let us assume that you are playing with Lego toys. So, you want to make a new toy. So, whatever toy you would have made using the Lego pieces, so you have to break the whatever toy you would have made. You require energy to break the bonds. So this I am denoting by EB, and because this is the energy which you would be put in the system, which you will be putting in the system, this would be positive. And on the product side, new bonds would be formed. Now, whenever new bonds are formed, energy is released. So this EF would be the system. EF would be the energy, which will be released when new bonds are formed. I hope this is making clear. Otherwise, you can look at the calculation, then it will start making sense. So what are we doing here? So on the left side, basically what we are doing is we are trying to break the bonds. So how many bonds would be here? For doing these kind of questions, you need a basic understanding of the chemical bonding. Otherwise, my take is that it becomes a bit difficult to understand. So chemical bonding, basics of chemical bonding is required. So CH4, because otherwise you won't be able to, for example, if I'm making these bonds, CH4 bonds, if you don't understand the basics of chemical bonding, how will you be able to visualize what is happening? So if you see here, there are 4 bonds which will be broken. This bond would be broken, this bond would be broken, this bond would be broken, this bond would be broken. So energy would be required. You'll have to put energy inside the system to break these 4 bonds. How we calculate this is that this is the amount of energy, this is the positive energy that will be required. I'll be multiplying this number by 4 because I am breaking 4 bonds. So I hope this is making clear, and this would be positive, and that is why you see this number 4 CH bonds I am breaking. This is the energy which is required to break the bonds. So 1640 kilojoule energy would be required to break the bonds of CH4 of methane. Now let us look at the next reactant that we need to bonds where we need to break. So this is a bond that I'll need to break. This OO bond that I need to break. It is mentioned here. Now, if you see, there are 2 moles of oxygen molecules that I have to break. So I'll have to give energy. The energy would be multiplied by 2 because there are 2 moles of oxygen molecules which I am breaking. So that is why you see here 2 the calculation is 496 into 2 is 992, and 4 into 410 is 1640. So what I'm trying to tell you is that 2632 kilojoules energy would be put in the system. 2632 amount of energy would be put in the system to break the bonds. To break the bonds of the products on the left side. I hope this is making clear, because see, this is a fairly simple topic. At least one question comes in the chemistry exam, and once you understand the logic, if you understand the logic of at least one question, one numerical, you'll be able to do all the numericals. And as I understand, this question, this numerical, this enthalpy calculation is repeated in class grade 11 also. So spend some time to understand how this works if you plan to take chemistry again. So I've calculated that 2632 amount of energy would be required to break the bonds. Now I come towards the product side. Now, if I look at the product side, see, this is how, if you want to, we can ignore the bonding for a while. So let us assume that if you don't understand bonding, then maybe you'll get some hint when you look at these bonds. So, for example, if you are the kind of student who doesn't understand single, double, triple bond, let us assume, then you can get a hint from here that if you are looking at CO2, then these are the kind of bondings which will be there. So there will be double bond on both sides of carbon. And the point that I'm trying to make here is that these are the bonds. So this is one bond which will be formed. This is another bond which will be formed. When one bond is formed, there is 805 moles of kilojoules of energy which is released. Now I am forming two bonds. So because energy is released, it is negative, and this has to be multiplied by 2. So 1610 kilojoule of energy is released. Please understand that when new bonds are made, energy is released. So 2CO, because 2CO bonds are being made, so this is the amount of energy which is released. Now let us look at H2O. Again, let us assume that you don't understand bonding, but if you look at you'll get hint here. So this is what will be happening in H2O. So there'll be a oxygen, hydrogen, hydrogen. Now if you look carefully, now this is where you need to be a bit careful. This is the one bond of OH. This is second bond of OH. So each H2O molecule has two bonds, two OH-OH bonds. When energy is released, negative sign is used. But then there are two moles of H2O. So this has to be multiplied by 2. And the whole has to be multiplied by minus 460. So this answer would tell us that minus 1840 kilojoule of energy would be released. So here minus 1610. Here CO2 minus 1610 kilojoule energy was released, and here minus 1840 kilojoule of energy is released. So we add these two. This is the energy which will be released. So minus 3450 kilojoule of energy is released. So in our system, 2632 was the energy that was required to break the bonds of the reactants. And when the products are formed, minus 3450 kilojoule of energy is released. So if you see net that we had predicted, net energy is released in the system. And we just have to calculate this minus 3450 plus 2632. So 8431. Minus 818 kilojoule. Minus 818 kilojoule per mole. Always remember that the unit of enthalpy is kilojoule per mole. So this is the energy which is released from the system. And of course, when we started the question, this is what we had expected. So, my suggestion to you would be that spend some time to understand the logic of this question. I have even provided you with hints that even if your bonding is not chemical bonding topic is not very clear, when you look at the bond energy, you can get hint about the the kind of bonding which will be there in the molecule. And otherwise, this is a fairly simple topic, doesn't require much. And another thing that you need to understand is that you need to look at how many moles of the molecules are there. So this is another critical thing that you need to understand. And if you haven't understood, I'll request you to look at it again because this is a critical question. At least one numerical will come in the exam. So let's move to the next question. Let's move to the next numerical. Question. This is a pretty interesting question. Very interesting question because here the enthalpy of the reaction is already given. So usually in the rate of reaction calculations, we have to find the enthalpy of the reaction. But here the enthalpy is given. So and what is the question about? Let us look at it carefully. So table 4.2 shows some bond energies. So the bond energies are shown, and let's carefully look at the bond energies. So C triple bond O, C triple bond O is here. So this is the bond energy. ClCl, this is the bond energy. CCl, this is the bond energy which is given. Now, if you look carefully, the C double bond O, this is the bond energy which we need to calculate. If you look at the question, use the bond energies in table 4.2 and value of delta H for the reaction to calculate the bond energy in kilojoule per mole of the C double bond O bond. So that is why this is an interesting question. The enthalpy is given. We have to find the bond energy of a particular bond. So how do we go about doing this? The method remains the same. First, we'll have to calculate the energy which will be required to break the bonds of the reactant. So we'll first find the energy that will be required to break the bond of the reactant. This would be the energy which will have to be put in the system. Then we'll find the energy which is released when the reactants are formed. And here what we'll assume is, like we do in algebra, we'll assume that this bond energy of C double bond O is X. We'll use this X, we'll form an equation like this, and then we'll calculate the value of X. This X 740, which I have calculated, this would be put here. So let's start. So the first thing that we need to do is we need to calculate the bond energy required for the C triple bond O. So C triple bond O, this is the amount of energy. This is C triple bond O. This is the amount of energy which has to be put in the system, 1075. Then if you see the second bond is ClCl. This is for ClCl also they have given the bond energy which is 240. I have put it here, 240 kilojoule per mole. So for the left hand side of the equation, let's focus only on the left side of the equation. For the left hand side of the equation, that is for the reactants, the total energy which is required to break the bond is 1315. 1315. How did I get 1315? I added 1075 and I added 240. So this is the amount of 1315 amount of energy is required to break the bonds of the left hand side, the reactants on the left hand side. Now when I look at the right hand side, I know I have the bond energies for CCl. These are the bond energies I have, but I don't have the bond energy for C double bond O. So I assume it to be X. So for CCl, because I am breaking, because bonds are being formed, this is the energy which is released. So minus 2 into 340. And for, as I've already told you, for C double bond O, this is the amount of energy which is released. So the total energy which is released is minus 680 minus X. So this is the amount of energy which is released, minus 680 minus X. Minus 680 minus X. Now, the energy which was given to the system was 1315. The energy which is released is minus 680 minus X. So what is the net energy which is released? So for calculating the net energy which is released, I will use this minus 680 minus X plus 1315. So 635 minus X is the amount of energy is the amount of net energy which is released. And then I equate this 635 minus x to this minus 105. I hope this makes sense. So, like we are doing in the other questions also, see here we just have, in the other questions, usually what happens is that we have to calculate the delta H. But here delta H is given and one of the bond energy has to be found. The sequence of events remains the same. Whatever the bond energy has to be found, assume it to be X and follow the same steps like we have been doing before. And just in the last step, you just have to equate that X to the given delta H. That is the only thing which is new here. So when I calculate the value of X, basic mass I'm using, so 740 is the amount of X. So here, the bond energy for C double bond O is 740 kilojoule per mole. Yeah. Now let us look at, we have done all the calculations and now let us look at what they are asking. So calculate the energy needed to break the bonds in the reactant. So the energy, total energy which is required is plus 1315 kilojoule. That we had calculated because all the energies are given. So this would be plus 1315 kilojoule. Calculate the bond energy of the C double bond O. That also we have calculated. That is this 740 kilojoule. This is this 740 kilojoule. And finally, what is the energy released when bonds in carbonyl chloride are formed? So finally, they are asking, because you will require the bond energy for C double bond O. So what they are asking finally is that boss, what will be this energy? So easy way of doing this is you had already calculated this minus 680 minus X. Now you know the value of X. So minus 680 minus 740. So this would be 8412 1 minus 1420 minus 1420 minus 1420 would be this amount of energy would be released when the carbonyl chloride would be formed. And now let us audit whether our answer is correct. So this is the energy which is released when the reactant is formed. The energy which is required to break the bond is 1315. And the net energy is minus 105. This is the enthalpy of the reaction, which is equal to what is given as the answer. So this is a bit different from the other questions. Very interesting question. This was asked in February, March 2025. So last year in the February, March session, they had asked this. So hope this makes sense. Let's move on to the next question. Looking at a few enthalpy reactions now, where we have to calculate the enthalpies, and more or less in every chemistry paper, this question comes. So it's a pretty important and a fairly easy topic that you can prepare for the exams. I'll be doing 3 to 4 numericals. Let's start. So iodine and bromine react at high temperature to form iodine monobromide. This is a reaction which is shown the structure of the molecules, and this is the bond energy. Now, once you understand the logic, this is a very simple topic. All that you need to understand is that it's a very commonsensical approach. If you want to break something, you need energy. So, for example, let us say there's a chair that I want to break. Now, if I want to break a chair, I need energy to break the chair. So similarly, when you are breaking the bonds, you will require energy to break the bonds. For example, in this case, of course, you should have some idea of the chemical bonding. Not very deep idea, but basic understanding of chemical bonding is required, is a prerequisite. For example, if I2 is there, so 2I would be bonded together. So I'll have to break the bond of these 2I. For breaking the bond, this is the energy which will be required. I will have to put that energy in the system. So that is why to break. And please notice that only one mole of I2 gas is being broken. So Here I will be breaking 1 mole of iodine molecules. Here I'll be breaking 1 mole of bromine molecules. But here if you see, I'll be breaking 2 moles of IBR, iodine monobromide. So what I'm trying to imply here is that you should be very clear about the coefficient here, because that coefficient would imply the number of moles which would be required. Because if you see here, it is bond energy in kilojoules per mole. It is per mole. So here I have to break 1 mole of iodine molecules. So I will be requiring 150 kilojoule per mole. So I haven't written kilojoule per mole. You can write it here. Then next I have to break 1 mole of bromine gas molecules. So for that I will require 193 kilojoules. So total, this is the amount of energy which I require to break the reactants. So to break the reactants, this is the amount of energy which I'll require. I'll have to add that. So 3, 9, 5, 14, 1, 2, 3. 343 kilojoule per mole of energy I have to give in the system to break the bonds. Another example, if you want to take, if you have to break bones, if you want to break somebody's bones, you have to put in some energy to break the bones. So bones, bonds, same thing. Now when we come to the reactant side, the inverse would be taking place. Now what will be happening is there would be bond formation. 2 moles of iodine monobromide is being formed. 2 moles. Now from these bond values can be used for breaking also, and when the bonds are made, this amount of energy is released. We just have to take care of the signs. So for example, in this case, the sign that we were using to break the bonds was positive. But when 2 moles of IBR would be formed, this amount of energy, 2 moles of IBR, this amount of energy would be released. So when 2 moles of IBR are formed, for 1 mole, 175 moles of energy. This is the sign that I'm using, because a negative energy implies that energy is released. You can imagine it like this. For example, this is the system. From this, energy is released, so the energy comes down. So to make when 2 iodine monobromide moles are made, 2 into 175 kilojoule per mole of energy is being released. So total energy which is being released is, this is the amount of energy that is being released. So this is the energy that is being released. This would be kilojoule per mole, but then this would be kilojoule. Similarly, this minus 175 is kilojoule per mole, but this is the energy, total energy which is now is leaving the system. So if you want to visualize, one way of visualizing this is that if this is the system, then the energy required to be put in the system would be 343 kilojoule, and then energy which will be released when the products are formed, the energy released would be 350 kilojoule. So minus 7 kilojoule, this would be the delta H. This is the amount of energy which is being released. This is the amount of energy which is being released. So this is a exothermic reaction. This is the net energy being released. Remember, when delta H is negative, energy is released. You can imagine it like this is the amount of energy which is being given out from the system. And all the systems which give out energy, they are exothermic reaction. A typical example is a combustion reaction. So combustion reaction, energy is given out. So what we understand is that 343 kilojoule of energy is required to break the bonds, and 350 kilojoule is released from the system. So another way, if you want to visualize, if this is the system, then you will require 343 kilojoule this energy would be required to break the bonds of the reactant side. You'll first break the bonds. Then when the bonds are made, then 350 kilojoule. This is the amount of energy which the system would release when the products are formed. So the net energy which is released, because in this case the negative sign is more than the positive side. So we will see that 7 kilojoule is the amount of energy which the system would release. So our answer would be delta H would be minus 7. They are asking for the sign also. So our answer would be minus 7 kilojoule per mole, and energy required to break the bonds. To break the bonds, plus 343 kilojoule would be required, and total amount released is minus 350 kilojoule. So as I told you, it's a this topic is fairly simple, and more or less one question would come from this topic. So let's do few more numericals. So let's look at the next numerical for calculating the delta H, the enthalpy change of a reaction. Iodine and chlorine react at high temperature to form iodine monochloride ICl. Equation is given, and structures of the molecules are IICl, ICl. So they are asking for the delta. Now this question is similar to the question that we have done before, almost same. So here iodine and bromine were reacting. Here iodine and chlorine are reacting. As I've told you before, here 1 mole of iodine molecules is being broken. So this is the amount of energy which will be required to break the bonds of iodine. 1 mole of iodine molecules here will have to first break the bonds of chlorine molecules, IIClCl. So we require energy to break the bonds. We require energy to break the bonds of II and ClCl. So the total energy which will be required would be, because it's an energy which we will have to put in the system. So it will be, because there are 1 mole of iodine and 1 mole of chlorine. So if you see 392 kilojoule is the amount of energy which is required to break the bonds of iodine and chlorine. Basically, the total of 392 kilojoule amount of energy is required to break the reactants first. That is another way of looking at the things. So basically, to break the reactants, bonds of the reactants, I will be requiring, to break the bonds of the reactants, I'll be requiring 392 kilojoule amount of energy. This has to be put in the system. But remember, when the products are formed, energy is released. When products are formed, energy is released. Because 2 moles of ICl, iodine monochloride, is being formed. Or when 1 mole of ICl is made, then 218 kilojoule of energy would be leaving the system. But we are making 2 moles. So that is why I multiplied by 2. So the total energy which will be releasing the system when 2 moles of ICl would be formed would be minus 436. After that, it is simple mathematics. So 392 kilojoule is entering the system. 436 kilojoule is leaving the system. So there will be net energy which will be released from the system. So that is why this would be an exothermic reaction. Delta H would be negative. So minus 436, 392, and the calculation is correct. Minus 44 kilojoule per mole. So now the question which is being asked is, calculate total amount of energy required to break 1 mole of I2. This is 392. This is 150. You will be writing 150 here. Sorry. So 150 kilojoule would be energy required to break the bonds of 1 mole of I2. And okay, and 1 mole of Cl2. So you'll have to add. So 392 kilojoule is, this would be the answer for part 1. Then they are asking, we'll write it here, 392 plus 392 kilojoule. Total amount of energy released when bonds are formed. So the energy which is released is minus 436 kilojoule. Minus 436 kilojoule. Calculate the enthalpy change for the reaction. Your answer should include the sign. So our answer would be minus 44 kilojoule per mole. A fairly simple question. You should have a basic understanding of the bonding, and if you do 3 or 4 questions like these, be able to do these questions in exam also. So let's